to this video lesson. Here we're going to be doing some practice questions on the 5 equations of motion, and we're going to focus on horizontal motion in this video. In this first question, we got an airplane which accelerates down a runway at 3.2 meters per second squared, so I will highlight that information. And it's in the forward direction for 32.8 seconds, that's important, until finally it lifts off the ground. Great. Determine the displacement traveled, or just displacement, I should say, this question. Displacement before takeoff. First step is to draw this out. Let's try it out. Let's say this is the runway and the plane has to start somewhere. So I'm not very good in drawing planes, so I'm going to draw a box instead. That's our plane. And our plane is going to start with a certain velocity. We're going to call that velocity 1, and this is going to be stage 1. And it's going to move and accelerate forward. So we're going to take this side to be my positive in this question. And I'm going to highlight that because that's important. And we're going to accelerate forward. So with acceleration, I use this sign over here, the squiggly. And this is, actually, I might need a little bit more space. So I'm going to move this here and do the acceleration. This is 3.2 meters per second. So my units are also in meters and seconds. And that's it. So I'll write that out so then I don't have to write everything down here. And you can note that I'm not actually putting an arrow on here because the direction is indicated by the arrow. I have this, so I have the acceleration is accelerating forward, and then finally it lifts off the ground. So at some point it starts to lift off the ground, and at this point, just before it lifts off, it's also going to have a velocity. I'm going to call that velocity 2, and I'm going to call this stage 2. From here to here, obviously there's going to be a displacement in this direction. So this is going to be the displacement from 1 to 2. And we're also going to have change in time from 1 to 2 as well. And that's it. So let's see what informations we can fill out and which ones we can't. So initial speed, we're going to make an assumption that it starts at rest. It doesn't say in the question, but an airplane usually starts at rest and then it moves and then it reaches a final velocity. So final velocity is not given to us, so this is a question mark. The displacement is not given to us, but the time and the duration is, so that's 32.8 seconds. Now let's see if we have labeled everything in the question. We basically, direction forward is labeled, stage 1 and stage 2. This is only a 1 interval type question. Sometimes you would have more stages. In this case, this is it. Velocity 1, so there's 5 pieces of information: velocity, initial velocity, final velocity, acceleration, displacement, and time. They are all labeled, and everything that has that is a vector quantity also has its vector shown, so we know which direction they're pointing at as well. This is a beautiful system diagram. We're ready to move on to stage B, which is our graphs of motion. We're going to think about a motion diagram. I'll do the motion diagram right. Actually, no, I will do it here. This is the forward direction. And then we are going to have 3 graphs: position time, velocity time, and acceleration time. All right, so for the motion diagram, we're going to start slow and get faster and faster as we go because we're accelerating in that direction and our velocity is in the same direction. And if that's the case, we're speeding up. Um, and in terms of our velocity, we are going to start at 0 at stage 1, and we're going to move in the positive direction. We're moving in the forward direction. That means our velocity is going to be in this region. So I'm going to put stage 2. I'm going to connect them using a straight line because we're going to make an assumption later that we have a constant acceleration. In terms of getting my acceleration graph, well, uh, the slope of a tangent is consistently positive, and it's got like a medium value here. We know what its value actually is, but here again, we're sketching the graphs, we're not putting all the values in. But we know the acceleration is 3.2 throughout the whole situation here. And then we got our position time graph. So our position time graph, let's assume that we're starting at the reference point, and we're going to end up somewhere to the right of our reference point, which is in the positive forward direction. And this is stage 1, this is stage 2. In terms of how we do our curve, in the beginning, our velocity is 0, so the slope here needs to be a horizontal line, and the slope at the very end is a positive, sorry, velocity is positive, so the slope here is also positive. Connect this using a nice curved line, and this gives us a very good idea about how the motion looks like. We know the object is speeding up through this graph. We know that the velocity is always in the forward direction. It's not moving back. We know the acceleration is constant, and we have a nice curve indicating its position as well. And then we get to part C, which is the word, any assumptions we're making, and the description of the motion. We can do the description of motion basically based on here, but I'm just going to label the assumptions in this particular question. You can always practice writing the motions, especially because you have the beautiful graph labeled here. For the assumptions, two major assumptions we're making here. One is that there's no air resistance slowing it down or wind moving it forward. So these are negligible. And then we're making an assumption also that based on those acceleration, actually not just based on those, but basically acceleration is constant. And that means the acceleration throughout this whole procedure doesn't change. In this case, this is very important in this case because usually if you have a plane, right after people get on it, it starts moving back in different direction until it adjusts its direction, and once it's adjusted its direction, then it starts to move in a straight line, and during that time it's usually moving. So this assumption, very important. The next section is section D, which is our mathematical representation. And in this one, what we do is we look at our information and figure out which equation we need to use to solve the problem. So we got the information that we have. We got initial velocity. We don't have final velocity. We have the acceleration. We have the time, and we're trying to find the displacement over here. So we're looking at an equation which has everything except the final velocity. So this first one has a final velocity, the second one doesn't have a final velocity. That's the one we're going to use. So I'll just write the equation here. The equation is displacement is equal to initial velocity multiplied by the change in time. Initial velocity for us is the velocity at stage 1 plus 1/2 of the acceleration times the change in time squared. I have the equation. Now I'm going to plug all the information that I have in. So Initially, my velocity in the beginning is 0. 0 times any number is just 0, so I can just cross that out right away. So then displacement will equal to 1/2 my acceleration. So I'm accelerating in the forward direction. That's consistent with my sign convention, so I'm going to use a positive value. And my time is 32.8 seconds, and I have to square that, and I put that on my calculator. I will get 1721.344, and I have to look at my number of my number of significant figures. I have 3 here, I have 3 here, and that's the lowest that I have, so my final value needs to be rounded to 3 significant figures, and that's 1720. In terms of direction, in terms of my units that I'm using in this is meters and seconds, so it's meters, and my direction is forward. Part E is the evaluation, so let's talk about that a little bit. The final answer that we got was approximately 700 meters, and a typical runway, I actually had to do a research on this. So runways usually require at least 1,800 meters distance. That's a lot. That's 1.8 kilometers before the plane actually takes off, but we give that space so that they reach the speed that they need before takeoff. So this is actually very reasonable based on this. Again, I had to Google this to kind of figure out. So if you're doing your questions on homework questions, you can kind of like get a little bit of an idea about how things work just basically on with a little bit of a Google search. And again, so this makes sense in terms of our taking away our assumptions. If we have less air resistance, it would travel more during that time. If there's wind, depends on the direction of the wind, it could push it towards or away, and that will have different effects. And acceleration is constant, so we are making an assumption that the plane is just moving forward, and that acceleration during this whole time is constant, but in reality it isn't. There are bumps in the road that might slow it down. The plane right at the beginning, when people get on it, it goes back and forth. So a lot of assumptions there, but and each one will have a different effect on the final answer. So this is our answer to the very first question. Let's try the second one. In this question, we get a car that starts from rest. Okay, this is nice. At least it mentions that it starts from rest. It accelerates uniformly over time for 5.21 seconds, and we get a displacement of 110 meters in the east direction. And we want to determine the acceleration. Let's draw this situation out. This is part A. So we got a car, and I am going to take east to be positive in this direction, and I'm going to highlight that right away so that we have it. And we got a car. Just for sake of simplicity, I'm going to draw it as a box, and we are going to be at stage 1 for the car. It's going to accelerate uniformly over time, and it's going to get to stage 2 at some point, and this is stage 2. We're going to have an initial velocity here. We're going to have a final velocity here. And we're going to have a displacement. So the displacement is from here to here, and that is the displacement from 1 to 2. It's going to take a certain amount of time here, and we're going to make an assumption. Well, we know that it's going to accelerate in this direction, so I'm just going to have that in. The reason we know that is because it starts at rest, so we're given that set of information. Rest means that initial velocity at initial stage it's at 0 speed, and then we got the acceleration. We don't know what that is. but we know that it is in this direction because it's speeding up um, in order to be able to go in that direction. 5.2 seconds, it's the time, so I'll write that here. And the displacement is 110 meters. Note that the direction of my displacement is in this direction. I try to align them with my positive sign convention. And my units here are, I'm using meters and I'm using seconds. Good. And final velocity, I don't know. The question we're asked to find is the acceleration. Do we have all the information in already? Let's check. We got 5 pieces of information: initial, final, acceleration, displacement, and time. We have all of those. All of my vector quantities do have the direction indicated by the system diagram here. And my time is here, and 3 pieces of information are also labeled here. We're ready to tackle this problem. Let's do part B, which involves a motion diagram and 3 graphs: position time, velocity time, and acceleration time. And again, these are only sketches, and you don't have to worry too much about all the details and all the numbers in them. So for the first one, we started it slow, and then we get faster and faster, and we traveled a certain distance. Assuming that, well, not assuming, we know that initial velocity is 0, and our final velocity, we're going to assume that it's going in the east direction because it displaced in that direction. And this velocity and this velocity are in the same direction, so this is in the positive direction, so my velocity is in this region. If the object ever went in the opposite direction, then we will have this region as well, but here we only focus on here. It's going to gain speed, so it's going to have a positive slope like this. And the acceleration is just the slope of the tangent throughout here. They're consistently a positive value. So this is stage 1, stage 2, stage 1, stage 2, stage 1, stage 2. And for the displacement, it's very similar to the last one. It displaces to the right. And initially my velocity is 0, so the slope here is 0, and my final velocity is positive, approximately medium, so I'll draw a positive tangent. I will connect them, and I will have this. Part C is any assumptions we're making, so assumptions, or you can describe the motion using your diagrams. Some of the assumptions here is that it's constant acceleration, and instead of acceleration, actually, I'm just going to put this in. Okay, so it's constant acceleration. In reality, it won't be. There might be bumps on the road slowing it down, the way the engine works, and it gains power. It's not going to be purely constant, but we can make an assumption that it's approximately constant in this case. And no air resistance or negligible air resistance in the case, and no wind kind of pushing it forward either. So those are kind of like the assumptions we make, and then we're going to do our analysis. We want to figure out what the acceleration of this one is, so that's what we're looking for. We have initial velocity, we don't have final velocity, we have the displacement, and we have the time. So I'm going to go in and look for an equation that doesn't have the final velocity. And similar to the last question, this is the one. This is the equation that doesn't have final velocity in it. So displacement is going to equal to initial velocity times the change in time plus 1/2 of the acceleration multiplied by the delta t squared. I'm going to plug in my values. Velocity 1 is 0, just like last time. That would cancel out this whole term because 0 times any number is just 0. And then my displacement is going to equal to 1/2. My acceleration is what I don't know, so I'm just going to leave it like this. And the change in time is 5.21 squared. I do apologize, I forgot I have to put in my displacement. And my displacement here is positive 110. I'm saying positive because the direction of the displacement from 1 to 2 is consistent with my positive sign convention. So I have that as 110. And now all I have to do is I have to rearrange and isolate for A and calculate it. So A, I'm going to multiply both sides by 2 and then divide it by 5.21 squared. And I'm going to put that on my calculator. Once I plug everything into my calculator, I get 8.10489, and then the value continues. So therefore, I have to look at how many significant figures my solution should be. And in this case, I have 2 significant figures here and 3 significant figures here. So my final answer should be good to 2 significant figures. So that's 8.1 meters per second squared. And my direction is in my positive sign convention, that's east. So this answer needs to be corrected to 8.1 meters per second squared in the east. So I like to box my final answer so we know what that is. And part E, the evaluation of this question. So this is a pretty fast car. Basically, when we're looking at kind of speeds, if you have a car that can accelerate from 0 to 100 kilometers per hour, then its acceleration in 3 seconds, then its acceleration would be about 9.2 meters per second squared. If it can do it in 5 seconds, then we're talking about acceleration of 5.56 meters per second. And I'm just doing some Google search to see that. Obviously I can also calculate it by putting the values into one of these equations and finding them out. But just for your general information, a typical car like let's say we got a car that can accelerate from 0 to 100 in 6 seconds or even 5 seconds. We're talking about an acceleration of about 5 meters per second. So 5 meters per second squared is typical for accelerations from 0 to 100k. But in this case, they are going. Well, this car is actually. I tried looking at the final velocity, and the final velocity was over 100. And if you have a car that's fast enough, if you have a car that can accelerate to 100 kilometers per hour within 3 seconds, then you get approximately 9 meters per second squared of an acceleration. So it's possible. It's rare. You need to have a very expensive car for this to happen, but it is possible. So we can say it is realistic for faster or more powerful cars. Good. Yeah, so in terms of it is definitely possible. Again, if you were to add air resistance, then the acceleration would be reduced. If we had wind going in the same direction as the car in a very, very fast speed, then it could affect the acceleration and actually increase it. And yeah. So those are kind of like some of the stuff that you're looking for. And in constant acceleration, it's very challenging to get at a constant acceleration, but it is a good assumption because in general, um, there isn't that many bumps and stuff happening, and the engine itself, yes, it's not going to accelerate constantly all the time, but for the short amount of time, we can make that assumption. Let's look at the next question. In this question, we have a bullet which leaves a rifle with a muzzle velocity of 521 meters per second forward. While accelerating through the barrel of the rifle, the bullet moves a distance of 0.84 meters. Determine the acceleration of the bullets. Okay, we can do that. I'm going to draw. Let's say this is the barrel. The barrel obviously will be kind of like a cylinder. And in this cylinder, you have a bullet. I'm going to draw the bullet with a box. And it's going to be at stage 1, and then it's going to be at stage 2 at the very end. Stage 1 is going to have a velocity 1. That's going to be our initial velocity, and it's going to have a final velocity at the very end. Initially, in the gun, the bullet is going to be stationary, so it's not going to be moving. So initially, it's going to have a velocity of 0. And then at the end, it's going to have a velocity of 521 meters per second based on the information that we're given. I'm going to do my sign convention here, and I'm going to take right to be positive, so that's forward. And I am going to highlight it. And the units that I will be using in this one are meters and seconds. I do like using fundamental units in general, and since I've kind of like labeled it here, then I'm not going to label everything here again. You can, if you want, you can say this is meters per second, this is meters per second, but I just want to be concise and consistent here. Okay, the other information that we need, we have our final and initial velocity. We need our acceleration. I'm going to make an assumption that it's accelerating in this direction. Doesn't really matter which way you do it. You might get a negative value, and that would mean that it's accelerating in the other direction, but I'm going to make an assumption that it's accelerating that way. And for my displacement, from here to here, notice again, I always use the front of the box to connect. I have seen students who do front and then the back. That's not proper. You got to do front, front, or middle to middle, or back to back. And then displacement from 1 to 2, this is the displacement from 1 to 2. Again, I don't have the arrow sign here because the arrow, this is kind of like the magnitude of this vector over here. And this is going to be, do we have it? Yes, we do. It's 0.840 meters, so I'll write that down. The time doesn't have an arrow, so you see my arrows. This one is for this one is for this one is for this, and this one is for this. The time, we don't know. And the acceleration, we don't know. Do we have all the information in here? I have my event 1, when the bullet is stationary, event 2, when it's moving out of the muzzle. We have the initial speed, the final speed, velocity, acceleration, displacement, and time. So all of the information are given. And if I were to just look at this diagram, I could say, okay, object initially is at speed 0 or at rest. It travels for a displacement of 0.84 meters forward, and its final speed is 521 meters per second forward. So I can get all of the information from the question from my diagram, and that's what I want. Stage B. So this is stage A, and stage B, I am going to have a few graphs. And these are time in this axis, and we get position, velocity, and acceleration here. And we're going to start off. The object starts at 0 velocity, and then it gets faster. So for my motion diagram, the dots get the spacing between the dots increase. For velocity time, I start at velocity here, and then my final velocity is in the same direction as my forward. That's in the positive direction. Connect them using a nice straight line because we're going to make an assumption that it is constant acceleration. The slope of this line is positive throughout, so the acceleration is always positive. And for my displacement, we're going to start at the reference point. So I'm going to label 1, 2, 1, 2, 1, 2. Start here. We're going to end to the right of the reference point. So I'm going to be somewhere in the positive region here. And in order to figure out the curve, in the beginning, velocity is 0, so the slope here is 0. And at the very end, the velocity is positive, medium. That's going to be a slope like this. Connect them using a nice straight line, and I get this for my position time graph, and that's stage 2. My word representation is going to be my assumptions. So I'm gonna assume a constant acceleration in this case. When there's different mechanisms in rifles, sometimes they curl and they move in different direction, meaning that they're definitely not going to have a constant acceleration because they keep changing directions all the time. In different ways, back and forth, back and forths. But on average, we can kind of assume that they have a constant acceleration. We're also going to make assumptions that there's no air resistance in there. Good assumption. There is well, I mean, there is going to be drag force as the bullet is moving in that direction, because inside the barrel there's air particles, and as this is moving, they're going to compress more and more, and that's kind of like you get a sound coming off after the end. So you get all that air being pushed out very fast. So we're assuming that there's no air resistance. That's a big assumption. We're going to assume that there's no wind pushing it forward. That's a very good assumption because in the beginning, obviously, there's going to be a force coming from some source here that pushes it, but after that, we're just going to assume that that's the force that's pushing it, and there's no extra wind pushing it in addition to that initial force. Now let's do part D to find what are we trying to find? We're trying to find acceleration, so this is what we're trying to find. We have this initial velocity, final velocity, and the displacement. So I'm going to look at my equations. What we don't have is time, so I have to find the equation that doesn't have time. This one has time, time, time. This one doesn't have time. That's what I'm going to choose. And this one says that the final velocity, my final velocity is my velocity 2 squared is equal to the initial velocity, which is my first one, plus 2 times the acceleration from 1 to 2. That's the average acceleration from 1 to 2. You can draw the arrows here. This is 1 to 2. And the displacement from 1 to 2. Good. Let's do this. The final velocity is going in the same direction as my positive forward, so that's going to be 521 squared. That's going to equal to 0 squared. So that's just 0, 0. I'm going to just cancel it out. And this is going to be 2. My acceleration, I'm assuming that it's going in this direction, and this is also positive, so I'm just going to use a positive value. And my displacement, I'm assuming, well, I know that my displacement from 1 to 2 is in this direction. That's a positive direction, so I'm going to put a positive value here of 0.84. I'm going to rearrange for my acceleration, and that's going to equal to 521 squared divided by 2.84. Make sure when you're doing this on your calculator, you do this squared divided by, put all of this within a bracket when you're putting it on your calculator. And the answer that I get from my calculator is equal to, I'll just write it here, 1615720, and then it just keeps going. And how many significant figures? So I have one set of information which is in 3 significant figures. My next set of information, 3 significant figures. So my final answer should also be in 3 significant figures. So I'm going to say approximately. This is going to be 16200 meters per second squared, and my direction is going to be in the positive sign convention, which is forward here. I can also write this in scientific notation. I'm just going to say or because both answers are definitely acceptable. That's 1, 2, 3, 4. I forgot a 0 here. 10, 5 forward. Just to make this look more reasonable, because I have to model things properly for you folks. I can't just tell you guys that you need to leave your that you need to have a space between your measurements and units and not do it myself. So that's kind of why I'm doing this. And I'm going to erase this as well because I forgot the unit here. This is meters per second squared, and that's forward. So that's my final answer. So one of these two. It just needs to be in correct number of significant figures. Doing some research on speed of bullets, pistols, acceleration can be, well, I don't know if it can be up to, but there are speeds of 4.5 times 10, sorry, accelerations of 4.5 times 10 to the 5 meters per second squared. This is much less. This is approximately well, 3 times less than that value. So this is pretty realistic in terms of whether it's realistic or not. In terms of how air resistance would affect it, well, if there was more air particles, so if the air density was more in the barrel here, then there would be more air particles which would slow it down as it goes, so they would have a slower acceleration and a little bit more frictional kind of resistance from the air particles. And the constant acceleration, I guess it's pretty significant for depending on what mechanisms we're using. If we're using a mechanism where there's a rotation here, then it's not the greatest assumption, but it's okay. Maybe on average it accelerates pretty constantly. But if it is just a straight shot, then it might accelerate a little bit faster in the beginning and accelerate a little bit less at the end. So yeah, different things that we need to keep into consideration, but in general, these are not bad assumptions. Let's try the next question. We got a race car that accelerates uniformly from 46.1 meters per second. That's pretty fast. It's a race car, so that's okay. To 18.5 meters per second. And they're both moving in the south direction. And this happens in 2.47 seconds. And we want to figure out the acceleration and the displacement. Okay, this time we are calculating two different components. So stage A, I'm going to draw out this situation, and we're going to have a race car. It's going to start here, and I guess I don't need this much spacing. I want to do my sign convention here. I'm going to take this direction to be south, and that's going to be my positive direction. And I am going to highlight it. And since everything is given in south, it's a lot easier to take south to be positive. Now, okay, let's do my stages. This is stage 1 of the car. This is stage 2. Initially, it is at velocity of 46.1. My units here are meters and seconds. And then it takes I'll just label a few things here. This is v2. This is the displacement from 1 to 2. I'm going to assume it's accelerating this way. We'll see what happens there. And we got the time. Okay, so these are the informations that we will need in this case. Velocity 2 is 18.5. The time it takes for it is 2.47. Maybe I should have highlighted this. I do apologize, I forgot. And those are all the information that we're actually given. So the time is 2.47 seconds, and we don't know what these equal to. In this case, we're making an assumption that acceleration is going in this direction, and that's fine. We know that it shouldn't because our initial speed is in this direction, and it's slowing down, and in order for it to slow down, acceleration should be pointing in the opposite direction. But whenever we're doing these types of questions, it's nice to align everything in the direction of your positive sign convention. It's not necessary, but it will help sometimes. But anyways, let's do the question and see what we get. Let's do part B first, which is our motion diagram, our displacement time, our velocity time, and our acceleration time. So this is time, position, velocity, and acceleration. And let's start. Initially, we are moving fast, and then we are moving slower. So that's 1, and that's 2. And for our velocity, I always do velocity next. Velocity starts at 46. It doesn't end at 0. It ends somewhere here. I'm going to connect them like this. This is stage 1. This is stage 2. My acceleration, the slope of this line is negative all the way. So it's going to be a negative consistent slope here. And for my position, I start at the reference point and I end in the south direction. So I end somewhere here. And in terms of the slopes of my values, initially I have a very, very steep slope. And later on, I don't have a 0 slope, but I have a less steep slope. So to connect them, it's going to start like this and move like that. That's kind of a good indication. It's not the best. It kind of looks straight here, but that's the best I can do with the spacing that I have. Now, does this make sense? Let's make sure that everything makes sense here. So initial velocity is high. At the end, it gets lower. The time it takes here is 2.4 seconds. I'm not labeling that, and that's fine. With the acceleration, we can see that it's a negative acceleration. So even though we assume the acceleration is going this way, it's negative, meaning that it's actually going in this direction. And that makes sense because if velocity and acceleration have opposite directions, the object is slowing down. Beautiful. Let's move to section C, which is our assumptions. Constant acceleration. We're assuming that there's no air resistance and no wind kind of pushing it forward either during this motion. We need to find 2 pieces of information in this case. I'll do part D here this time, and I'll use 2 different colors for the 2 different sections. So first of all, this is section D, and in the first part, we wanted to figure out what is the acceleration. So we want this. We have velocity 1, velocity 2, the time. What we don't have is the displacement. So I'm going to go look at my equations. The first one here doesn't have displacement, so that's the one I'm going to use. So I got final velocity is equal to the initial velocity plus a delta t. I'm going to put the values in. Sorry, I'm going to change it. This is velocity 2 is my final, velocity 1 is my initial, plus this is the acceleration from 1 to 2, multiplied by the change in time. Velocity 2 is 18.5, velocity 1 is 46.1, plus the acceleration, multiplied by the time of 2.47. Notice that what I have here, I could have just rearranged everything right away and used that. And I often do that, but sometimes for presenting it, I will plug in the numbers right away. So I'm going to rearrange now. This is going to be acceleration from 1 to 2 is equal to 18.5 minus 46.1 divided by 2.47. These are in brackets when you're putting it on your calculator. And I will get negative 11.174, which is approximately negative, oh yeah, how many significant figures? 3, 3, 3. My final answer should also have 3. So that's 11.2 meters per second squared in the south direction, because that is my positive sign convention. It's negative because we assumed it's going this way, but when it's negative, it means it's going in the opposite direction. That's good because velocity and acceleration have opposite signs, and therefore the object needs to be slowing down. For parts, for this part, I'm also going to do we also need to find the displacement, and to find the displacement, I need an equation that doesn't have acceleration in it, because I have these informations. So this one has acceleration, 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 acceleration. I'm going to use this one. And just so that I have a little bit of space here, I'm going to do that here. So I will use the displacement is equal to the initial velocity. In our case, the initial velocity is v1 plus the final velocity, for in our case, that's v2, divided by 2 multiplied by the change in time from 1 to 2. Okay, I got things ready to go. I just need to plug in the values here for the displacement, so that's nice. Velocity 1 is 46.1. Velocity 2. And sorry, in terms of signs also, I'm using positive because this direction and this directions are the same. So that's 46.1 plus velocity 2, which is 18.5. Divide that by 2 and multiply it by 2.47. And I will get approximately, so I'll just write the approximate value right away to 3 significant figures. That's going to be 79.8 meters, and my positive sign convention is south. So I'm going to leave that in, and here's my final answer here. And this was my final answer on the last one. You can notice that I have proper unit, proper direction, proper unit, proper direction. Do our answers make sense? So I did a little bit of research on this. So if you break from 30 meters per second to 0, then usually the distance is, depending on the break, this is a huge difference between these values. So it could be anywhere from really could be anywhere from 50 to all the way to 200. So this is, I would say, 70 plus. And in this case, you're going at a much higher speed at the beginning, but you're not really stopping. So this is going from 30 to 0. This is going from 46 to 18.5. So yeah. Yeah, so usually when you're at a higher speed, your distance, your stopping distance does definitely increase. But 70 meters for this, 80 meters for this, is pretty realistic because when you're going at a higher speed, um, your stopping distance increases significantly. So this is pretty realistic. Again, I had to do that through a little bit of research, otherwise I wouldn't have known. So this is kind of in terms of whether something is realistic or not. But going into my assumptions, assuming constant acceleration, definitely not. Usually when I wouldn't say definitely actually, but very likely it's not the case. It could be that you're accelerating less at the beginning and more at the end, and that's just because your brakes have an easier ability to stop your car at the very beginning. Sorry, when you're going slower compared to when you're going faster. Um, Other assumptions, no air resistance. If there was air resistance, it would actually help you, and if it helped you, you would brake at this distance would actually decrease, and your acceleration would increase. And if you had wind kind of like going with you, then that would increase the braking distance and change the acceleration as well. So I always think about what will happen if you were to remove one of these assumptions. Let's look at the next one. In this question, we got a car which is traveling at 22.4 meters per second. It skids to stop in 2.55 seconds, and we want to figure out what is that distance. Let's draw this out. We got this car, it's driving fast, it's driving at velocity 1 of 22.4, and then it starts braking, its tires catch on to the road, and then it's going to stop later. So let's say the car stops here, and we're going to have this as stage 1, this is stage 2, or event 1 and event 2. Speed here, it has stopped at that point, so this is going to be 0. And there's going to be a displacement from position 1 to 2. There's going to be a time that it takes for it, and there's going to be an acceleration as well. We don't know what the acceleration is. We are trying to figure out what the displacement is, but we know that this happens in 2.55 seconds. My positive, let's say traveling, okay, in this case we don't have any direction. Here we're kind of given the speed. We're going to make an assumption on the directions then, and we're going to have it going forward, and we're going to take that to be positive. Meters, we're using everything in terms of meters and seconds, and I'm going to highlight that, indicating those are my chosen conventions. Okay, looking back at the question, we can see that the object was traveling at 22.4 meters per second forward in that direction. It travels for 2.55 seconds, and then it stops at the end at 0 meters per second forward. Now we're going to go to section B. In section B, we have to do our motion diagram, our position time, our velocity time, and our acceleration time. Starting with the displacement, our object is moving, motion diagram, our object is moving fast at first and then slows down to 0, so the spacing between the dots gets smaller and smaller. In terms of velocity, start at a high velocity, get to a very low velocity, or zero velocity actually at the end. So this is stage 1, this is stage 2. Connect them using a nice straight line because we're going to make an assumption that acceleration is constant. Our acceleration is negative all the way through. So I'm going to draw that. Stage 1, stage 2, and it's constant. And in terms of displacement, taking this to be kind of our reference point, we start here, and we're going to end up to the right of our reference point, which is somewhere here. In terms of the curve itself, velocity is high. That means the slope here has to be high and it's positive, so it needs to be in this direction. And velocity here is 0. That means this slope of the tangent here, or the tangent line, needs to be a horizontal line. So connecting the two kind of starts in this direction, ends in this direction, connect the two lines, and we get a nice curve like this. This is stage 1 and stage 2. Looking at the signs and making sure everything works, and you can also kind of explain the motion if you want in section C here. You can see that the velocity is in the positive forward direction and acceleration is in the opposite direction, in the negative direction, and therefore it means that we will have the object slowing down because the velocity and acceleration are in the opposite direction. Let's move on to section C, some of the assumptions. We are going to make an assumption that their acceleration is constant. We're going to make an assumption that there is no air resistance and that there's no wind effect as well. So wind and air resistance, kind of different actually, because the wind could push back or push forward. And if the wind is pushing in this direction, the air resistance just increases. But if it's pushing us towards the direction, then the object will speed up more. And in this case, that would mean that it would slow down slower, and it would have a smaller acceleration. So these are kind of some of the assumptions we're making. Let's solve the question. I'm going to do section D here this time, and I'll put a bracket. It's a little bit easier to see the work. What am I trying to find? I am trying to find the distance. We're not even asked for the displacement. We just want to see how much the distance is. So this is what I'm looking for. I have initial velocity, I have the final velocity, and I have the time. What I don't have is the acceleration. So I'm going to go ahead and look for an equation that doesn't have acceleration. We got acceleration, 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 acceleration. This is the only equation that doesn't have it. So that's what I'm going to use. We got our displacement, which is equal to the initial velocity. Our initial velocity here is v1 plus our final velocity, which is v2, divided by 2 and multiply it by the change in time. And we just want displacement, so that's not too bad. We don't even need to rearrange anything. We got 22.4 plus 0 divided by 2. So 22.4 plus 0 is just 22.4 divided by 2. Multiply that by the time it takes, which is 2.55. And we put that on our calculator. We get 28.56 meters and in the forward direction. So I'll just put forward. And in terms of number of significant figures, 3 significant figures, 3 significant figures, so our final value should also be good to 3 significant figures. So this would have to be changed to 28.6 meters in the forward direction. We are not asked for the displacement, we're asked for the distance. So the distance then doesn't have the vector sign. It's going to equal to 28.6 meters, no direction. Now, in terms of whether or not this is realistic or not, I'm just going to change all of these like this. It's just doesn't look like there's a decimal point there. So we got 22.4 meters per second. If we were to multiply that by approximately 4, or 3 and 4, 20 times 3 is 60, 20 times 4 is 80. So our speed is somewhere in that, in between that in terms of kilometers per hour. In this case, when they hit the brake, the tires just stick, and then you get the tire marks in the floor. So there's huge amount of friction happening as this is going on, and you have this happening in a short amount of time, 2.55 seconds, going from approximately 80 kilometers per hour to 0. It kind of makes sense, especially if the tires have a high enough friction. As you will learn later when we talk about friction, you'll have a little bit easier time kind of figuring out whether these are realistic or not. But if there's enough enough friction or force of friction between the tires and the road, then this is pretty realistic for the time, because it takes 2.55 seconds. That's not bad. It's a short amount of time going from there to there. We're just going to kind of make assumptions in terms of orders of magnitude in this case. So anywhere between order of magnitude of 0 to 1. If it was anywhere between kind of like 2 to 10 seconds, it would have been fine. If this happened in like 0.5 seconds, then it wouldn't make sense. It's just too fast for a car to stop when it hits the brake at 80 kilometers per hour. For the time given, this is pretty realistic to have 28.6 meters of distance going. I would have thought it would be a little bit more, and the time it takes might be a little bit more as well, but this is okay. In terms of assumptions, if there is wind pushing forwards to this, then this distance will increase. If there is air resistance, it's going to stop the car even faster, so this distance is going to be reduced. And usually in reality, there will be air resistance, so this distance should be a little bit smaller, not significantly, but when you're traveling really, really, really fast, the air particles are hitting you. And as you slow down, they don't hit you, they don't have as much collisions with the surface of the car. So as you're going fast, there's more effect on air resistance than not. So, and yeah, so air resistance and acceleration in this case is constant. That's not the bad assumption here, because in this case, the tires are locked to the road and the car is just losing tire material as it's moving forward. So some of the bumps here might reduce the acceleration or just change the acceleration slightly, but on average, we could say it's pretty constant throughout the way. All right, let's move on to the next question. And the final question from this set of homework questions. I asked everybody to try this one out, so I hope that you can use the video to kind of make sure you're doing it correctly. Mr. S is running. He passes point A at a velocity of 3 meters per second and accelerates at a rate of 0.5 meters per second forward towards point B. The distance between points A and B is 20 meters. And we want to determine the time it takes for Mr. S to reach point B. Let's draw it out. We get a situation. Mr. S is going to be a box, and Mr. S is going to be, this is going to be stage A. This is going to be when Mr. S is passing point A, and this is going to be point B. Note that sometimes I label them using letters, sometimes I label them using numbers. It doesn't really matter. You choose what you're comfortable with. In this case, velocity initial, in this case, velocity A, or the speed at least, is 3 meters per second. It's in the forward direction, so forward is going to be my positive, and I'm going to have meters and seconds as my units. I'm going to highlight them. And in this case, as I'm reading this, velocity is 3 meters per second in the forward direction because the direction is pointing that way. Mr. S is accelerating at a rate of 0.5 meters per second, so towards point B. So in this case, it gives us the direction and it tells us forward. So we know that for sure it is in this direction, and acceleration here is equal to 0.5. And at point B, Mr. S, we don't know what velocity B is or the speed at that point is, so I'm going to put a question mark. We know that this distance from here to here, or the displacement from A to B, is going to equal to 20 meters. And the change in time is something we don't know. So again, as I'm reading this, now I'm going to look back and see if I can recreate the question based on this. So we got an object which is traveling at 3 meters per second. We know the unit for velocity or speed is length over time, so meters per second. The direction is in this direction, that's forward. The object is accelerating 0.5 meters per second squared in the forward direction, so that's this way. And then at stage B, we don't know what their velocity is, but we know that they travel 20 meters in that direction, and we don't know what the time is. So we have all the information, so we can always go back from here and see if all the informations are provided. Good. Let's do stage B of our question. So this is A, B, and in B we have a motion diagram. We have position time. We have velocity time. And we have acceleration time. This object initially is traveling at a certain speed, and it's just getting faster and faster as time passes. So I'm going to have my dots at a larger and larger distances as we go forward. In terms of velocity, my initial velocity is 3 meters per second, so it's not 0. It starts at somewhere positive 3, and it's in the forward direction, so I have it in the positive region. And as it accelerates in this direction, it needs to get faster. So at point 2, it's going to be somewhere here. Connect them using a nice straight line. And the slope of the tangents at these points are all positive, and they're constant too. The slope doesn't really change. So our acceleration is going to be constant in the positive direction. And for my displacement, imagining, let's say point A is right on our reference point, we're going to end up to the right of our reference point, so somewhere here. This is, oh, I'm writing A and, sorry, I should write A and B here, because that's what I'm labeling my, labeling my things as. You can do A, sorry, you can do 1 and 2 if you want, that's okay too. In terms of the way things are in this case, it's slightly different than usual. Usually, a lot of times I start at a 0 velocity, so I would have a 0 slope here, but in this case I have a bit of speed, so my slope initially is not 0, it's positive, but it's pretty small. And at the end, my velocity is getting bigger. That means the slope is getting steeper. So I'll have this as a steeper slope. And I connect the lines, so kind of start like that, finish like that, and connect them through a nice curve. And here we go. And that is our position time graph. Looking and making sure, just a few checks here. Velocity is in the positive region, acceleration is in positive. Positive and positive means the object is speeding up. In this case, that makes sense. The object is accelerating towards point B, so it is going to be speeding up. What are some of the assumptions we're making here? So that's part C. Assume. So based on our graphs, we can see we've assumed that acceleration is constant. We have assumed that we are going to assume that there's no air resistance and no wind effects. Good. These are pretty good assumptions. I don't see anything else at the moment. You can also just talk about, you can also say that we assume that position starts right at the reference point for our graphs, but it's okay if you don't include that in here. Next thing we're going to do is we are going to do part D, which is going to be which equation we're going to use to solve this one. So we got velocity initial, we don't have final velocity, we got the acceleration, and we got the displacement. So we're looking at an equation that doesn't have the final velocity in it. So this one has a final velocity, this one doesn't have a final velocity, and the rest all have final velocity in them. So let's do it. We got velocity, so we got the displacement, in this case the displacement from A to B is going to equal to the initial velocity, for us it's A, multiplied by the change in time plus 1/2 of the acceleration from A to B multiplied by the change in time squared. Okay, let's plug in the numbers here and see what we get. Starting with the displacement. Displacement is in this direction. That's consistent with my forward. I'm going to use a positive value of 20. And that's going to equal to the initial velocity. In this case, that's 3. So I'm going to plug that in. And I'm going to multiply that by the change in time plus, and sorry, I forgot, I use a positive because this is going in the positive direction, which is same as my positive sign convention. If this was going in the opposite direction, then I would have to use negative. And then plus 1/2. My acceleration here, so my acceleration here is 0.5. It's going in that direction, and that's also in the positive forward direction, so I'm going to use a positive value and change in time squared. Okay, let's simplify this as much as we can. So we got 20 is equal to 3 delta t plus 1/2 times 0.5 is 0.25, or 1/4, change in time squared. And well, we got the delta t squared, we got the delta t. We can't factor anything else. What we have here is quadratic equation. So for a quadratic equation, I'm going to set it up differently. I'm going to set it up so that everything with my variables are in one side. So sorry, everything is on one side. So I'm going to take the 20, which is my constant value, and I'm going to move it to the right side of the equation by subtracting both sides by 20. So I'm going to subtract both sides by 20 here. And when I do that, I'm going to get 0.25 delta t squared plus 3 delta t minus 20 is equal to 0. Let's make sure you understand the math here. We got 0.25 delta t squared. Because this is the delta t squared has the highest order of power, I'm going to put that first. And then we got the plus 3 delta t. If there's no sign beside it, it's a plus. So that's this region here. I'm going to take this bring it to this side by subtracting 20 from both sides. Subtract 20 from this side, I get minus 20. Subtract 20 from this side, I get 0. So that's kind of what I've done. I have to solve for delta t now, and this is kind of like a quadratic equation. So I'm just going to rewrite this. You can, if you want, if you're struggling a little bit, you can kind of say this is same as sort of changing. You can change delta t to x if that's what you're used to, and use the quadratic equation to solve this. So x is equal to negative b plus or minus square root of b squared minus 4ac divided by 2a. Let's write the equation. I'm just going to write the equation for that somewhere so you can see. So x is equal to, actually I'm going to write delta t in this case. Delta t or x, whenever you have a quadratic equation, is equal to negative b plus or minus square root of b squared minus 4ac divided by 2a. And we're going to use that idea. So our a value is whatever is being multiplied by the variable squared. This is going to be our b. This is going to be our c. Let's plug those in. So delta t is equal to negative, my b value is 3, plus or minus square root. B squared, that's 3 squared, that's 9, minus 4 times A times C. And I'm going to divide that by 2 multiplied by A, and my A value is 0.25. When I do this, I get 2 different values for delta t. One of them is when I minus, so one of them is when I add them, which I get 4.770 dot dot dot, and the other one when I subtract, which is negative 16.77 dot dot dot. I know that time, the change in time cannot be negative, so I'm going to cross that out. And I'm left with delta t being 4.77 dot dot dot. Now in terms of number of significant figures, I have 2, 2, 3. So my final should be the least of those, which is going to be 2. So I'm going to round my final answer to 4.8 seconds. And I'm going to highlight this. Now, I know that some of the students will struggle with a quadratic equation. You definitely have learned it before if you are in the Ontario curriculum, and this is a grade 10 content, so you need to make sure that you review that and that you understand it well. So try to look for videos on YouTube or other sources trying to find how to do quadratic equation well. In my physics course, once you reach this step, you can actually, if your scientific calculator can calculate or can use quadratic equation, you can go from here to this step right away and give me the final answer. So you can skip this step, the mathematical part, if your calculator can do it. So what steps should you include if your calculator can do it? Well, I'm going to shift to the right and show you. In this case, you have to set up the equation. So the least number of steps that I want to see for this is the first one. And then you will get, you can plug it in, you can say 20 is equal to 3 delta t plus 1/2 0.5 delta t squared. You can skip the next step right and go right into this one. So I'm assuming you can add the extra step, but you can definitely skip this one. And then from here, you can say using scientific calculator, The answer for delta t is 4.77 dot 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 or negative 16.77 dot dot dot. This cancels out, and delta t therefore is 4.8 seconds approximately. So you can, if you're really struggling with the math, if your calculator can handle it, use your calculator. This is a physics course, and obviously you do need to have certain skills in math, and I encourage you to be able to do it. But when it comes to efficiency, me as a teacher, I'm okay with you using your calculator to get to the solution. It is great math practice, but again, this is not a math course, and I need you to focus on the physics concepts more than the math. So that's kind of the solution there. Is it reasonable for this to happen? Well, let's see. So part E. Mr. S is initially running at 3 meters per second. That's an okay speed. So when we're talking 30 meters per second is approximately 100 kilometers per hour. So 3 meters per second, divide that by 10, approximately 10 kilometers per hour. So that's not bad. That's a good running speed, and you can kind of speed up and you can and it takes approximately 4.8 seconds to travel 20 meters here while accelerating. So that's not bad. That does make sense. That's not an issue. So I'm going to say that this is pretty realistic based on the speeds at the beginning and the short distance. Obviously, if this question, if the answer that you got was like, let's say 1,000 seconds, that would be unreasonable. If Mr. S is accelerating at 0.5, he should definitely um, get to 20 kilometers a lot faster than that. So keep that in mind. Another way you can think about it is that if Mr. S is traveling at 3 meters per second for about 5 seconds, that's 15 meters. And if he's accelerating in that direction, he should travel a little bit more. So if you had gotten 2 seconds, for example, 3 times 2 is 6, and that's less than 20 meters, so that wouldn't make sense. Or if you got a very large value here, let's say even 20 seconds, 3 times 20, if he was not accelerating, 3 times 20 is 60 meters. So if he is accelerating, 60 meters is a lot larger than 20, so that wouldn't be that reasonable. So you can kind of like look at what would happen if Mr. S was just not accelerating, how much would he travel, and now that he's accelerating a little bit, does it make sense that he is going faster? Okay, so that's good. And in terms of wind resistance, if there was wind resistance, the time it would take for Mr. S would be less, and that would kind of also result in a smaller acceleration. And if there's wind pushing him, then that changes acceleration as well. And is it okay that Mr. S was accelerating at a constant rate? Absolutely. That's not a bad assumption at all in this case. There isn't that many things that could kind of change that acceleration, so it's a very reasonable assumption. I hope that this video has helped you get a lot of practice with regards to these types of questions. Again, make sure you get good at solving the problem in all different steps. So you need a system diagram or a pictorial representation. You need physics representation. You need your assumptions, or you can also, in this case, think about the fact that you need to be able to explain the motions via your graph, and then the mathematical representation, and finally kind of talking about what will happen if we remove some of the assumptions. How would that change our final answer, and is our answer realistic enough? Thank you for watching.